Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving headfirst into a fascinating and honestly, somewhat unsettling development: large language models passing the Turing test. I'm still trying to wrap my head around it, really.
Unsettling? I think it's incredible. A major milestone. We've been working towards this for decades. To finally see a machine convincingly mimic human conversation, it's a game changer.
I wouldn't go that far. I think game changer is a bit strong. Passing the Turing test doesn't necessarily equate to understanding. It just means it's good at fooling people.
Exactly. It's like a really, really good parrot. It's mimicking, not understanding. And I think that's a crucial distinction, especially when we're talking about artificial general intelligence.
That's where my unease comes from, I think. It's the illusion of understanding. The UCSD team's achievement is remarkable, no doubt. But what does it actually mean? Does it mean we're closer to AGI, or just better at creating sophisticated chatbots?
I think it's definitely a step closer. Look, these models are incredibly complex. They're processing massive amounts of data and learning intricate patterns in language. That's not just mimicry. There has to be some level of internal representation, right? They're not just spitting back memorized phrases.
But what kind of representation? Is it a representation of meaning or just statistical correlations between words? That's the key question. Because if it's just statistics, then it's fundamentally different from how a human brain processes language.
And that's where the whole spatiotemporal aspect comes in for me. Language isn't just about words. It's about the context in which those words are used. It's about the spatial relationships between objects, the temporal order of events, and the relationships between actors. Current deep learning just doesn't capture that, I don't think.
Right. So let's break down what the UCSD team actually did for the benefit of our listeners who might not be as familiar. They trained a large language model, a very, very large one, on a massive data set of text and code. And then they pitted it against human judges in a Turing test scenario. The judges had to distinguish between the model's responses and those of a real human.
And it fooled them. That's the key. It fooled enough of the judges to be considered to have passed the Turing test. That means it was able to generate responses that were indistinguishable from human responses, at least in a textual conversation.
But the Turing test itself is problematic, isn't it? It's essentially a test of deception. It rewards the model for being able to imitate human conversation, not for actually understanding the topic at hand.
Exactly. Think about it. You could train a model on a data set of chess games and have it play chess at a grandmaster level. Does that mean it understands the strategy of chess, or is it just really good at pattern recognition?
That's a great analogy. It highlights the difference between performance and understanding. The model can perform the task of conversing like a human, but does it actually understand what it's talking about?
I think it's more nuanced than that. To perform that well, it has to have learned something about the underlying structure of language, the relationships between words, the rules of grammar. It's not just memorizing everything.
But those rules are implicit, aren't they? The model hasn't been explicitly programmed with rules of grammar. It's learned them from the data. And that's a fundamentally different kind of knowledge than, say, a linguist has.
And how does that knowledge translate to other domains? Can it take what it's learned about language and apply it to, say, solving a physics problem or planning a route through a city? I doubt it. It's all trapped within the language domain.
That brings up a key point: transfer learning. Can these models generalize their knowledge to new tasks and domains? That's a crucial characteristic of general intelligence, and it's something that current deep learning models often struggle with.
They're getting better, though. Transfer learning is a major area of research in deep learning. We're seeing models that can be fine-tuned for new tasks with relatively little data. It's not perfect, but it's improving rapidly.
And that's where I think the neuro-symbolic approach comes in. Instead of relying solely on data-driven learning, we need to integrate symbolic reasoning and knowledge representation into the models. We need to give them a framework for understanding the world, not just for mimicking it.
Yes, exactly. We need to give them a sense of space and time, a way to represent objects and their relationships in a coordinate system, so they can understand that a ball rolling off a table will fall to the ground, not float into the sky.
So, Sarah, can you elaborate a bit on neuro-symbolic AI? What are some examples of how it's being used, and what are its potential advantages over pure deep learning?
Sure. Neuro-symbolic AI is basically about combining the strengths of neural networks and symbolic AI. Neural networks are good at learning patterns from data, but they lack the ability to reason and represent knowledge in a structured way. Symbolic AI, on the other hand, is good at reasoning and representing knowledge, but it requires handcrafted rules and knowledge bases.
Right, like expert systems from the 80s.
Exactly. Neuro-symbolic AI tries to bridge that gap. One example is using neural networks to learn the rules of a game, and then using symbolic reasoning to plan a strategy. Another example is using neural networks to extract features from images, and then using symbolic reasoning to classify the objects in the image.
So, like combining the image recognition of a convolutional neural network with a symbolic representation of the objects in the image and their relationships.
Precisely. And the advantage is that it allows the model to reason about the world in a more structured way. It's not just relying on statistical correlations, it's actually understanding the relationships between objects and events.
That sounds promising. And Donald, how does your focus on spatiotemporal representation fit into this picture? Are you suggesting that we need to incorporate a kind of internal map into these AI systems?
Absolutely. Think about how humans navigate the world. We don't just memorize a sequence of actions, we build a mental map of our surroundings. We can represent objects and their relationships in different coordinate frames, egocentric from our own perspective and allocentric from a bird's eye view. And we can seamlessly translate between those frames.
Like a GPS in your head?
Yeah, but much more sophisticated. It's not just about knowing where you are. It's about understanding the spatial relationships between objects, the temporal order of events, and the causal relationships between actions and outcomes.
So you're suggesting that we need to incorporate something like a spatial reasoning module into AI systems? Something that can represent objects, their relationships, and their dynamics over time?
Exactly. And that module needs to be able to translate between different coordinate frames. It needs to be able to reason about the world from different perspectives, both spatial and temporal.
That sounds incredibly complex. How would you even begin to implement something like that? What kind of algorithms would you use?
That's the million-dollar question. I think we need to look to neuroscience for inspiration. How does the brain represent space and time? What are the neural circuits that are involved in spatial reasoning and navigation? We need to reverse engineer those circuits and translate them into algorithms.
That's interesting. So, you're suggesting a more biologically inspired approach to AI.
Absolutely. I think we've been too focused on brute force data processing and not enough on understanding the underlying principles of intelligence. The brain is the only example we have of a truly general intelligence system, so we should be studying it more closely.
And Otto, from your perspective, still believing in the power of scaling up deep learning, how do you see these different approaches, neuro-symbolic, spatiotemporal, fitting into the future of AGI?
I think there's room for all of them. I still believe that deep learning is the most promising path to AGI, but I also recognize its limitations. It's good at pattern recognition, but it's not so good at reasoning and representing knowledge. So good at reasoning and representing knowledge. So I think we need to find ways to integrate deep learning with other approaches like neuro-symbolic AI and spatiotemporal reasoning.
So you're suggesting a hybrid approach.
Exactly. We can use deep learning to learn features from data, and then use symbolic reasoning to reason about those features. Or we can use deep learning to learn the rules of a game, and then use a spatiotemporal reasoning module to plan a strategy.
I'm still skeptical that simply scaling up deep learning will get us to AGI. I think we need a fundamental shift in the core algorithm. But I agree that a hybrid approach is probably the most promising way forward.
So, let's talk about future research directions. If we were to give grants to researchers in this field, what specific questions should they be investigating? Sarah, what's at the top of your list for neuro-symbolic AI?
I think we need to focus on developing more expressive and flexible knowledge representation schemes. Current knowledge representation formalisms, like ontologies and knowledge graphs, are often too rigid and difficult to update. We need to develop new formalisms that can capture the nuances of human knowledge and that can be easily updated and extended.
So, something that can learn and adapt its knowledge representation over time?
Exactly. And that can integrate knowledge from different sources, including text, images, and sensor data. We also need to develop more efficient and robust reasoning algorithms that can handle the complexity of real-world knowledge.
Okay, and Donald, what's your top priority for research into spatiotemporal representation?
I think we need to develop a better understanding of how the brain represents space and time. We need to use neuroscience techniques, like fMRI and electrophysiology, to study the neural circuits that are involved in spatial reasoning and navigation. And we need to develop computational models of those circuits that can be used to guide the design of AI systems.
So, more direct collaboration between neuroscientists and AI researchers.
Absolutely. I think that's crucial. We need to bring together the expertise of both fields to make real progress on this problem. And we also need to develop new benchmarks and evaluation metrics for spatiotemporal reasoning. The Turing Test is not sufficient. We need more challenging tasks that require a deeper understanding of space and time.
That makes sense. Otto, what about you? What's the most important area of research in deep learning, in your opinion?
I think we need to focus on improving the robustness and generalization ability of deep learning models. Current models are often brittle and easily fooled by adversarial examples. They also tend to overfit the training data and fail to generalize to new situations.
Because they're just memorizing patterns, not actually understanding the underlying principles?
Partly, yeah. But it's also about the architecture of the models and the way they're trained. We need to develop new architectures that are more resistant to adversarial attacks and that can learn more generalizable representations. And we need to develop new training techniques that can prevent overfitting and improve generalization.
So, more focus on unsupervised learning and self-supervised learning.
Definitely. I think that's the key. We need to develop models that can learn from unlabeled data, just like humans do. That will allow them to learn more generalizable representations and to adapt to new situations more easily. Plus, the sheer amount of unlabeled data is magnitudes higher than what we have labeled. It could potentially drastically improve models with pre-training and unsupervised learning.
Okay, so to summarize, we've got a call for more expressive knowledge representation schemes for neuro-symbolic AI, a deeper understanding of the brain's spatiotemporal reasoning mechanisms, and improved robustness and generalization abilities for deep learning models. That's a pretty ambitious research agenda.
But a necessary one if we want to make real progress towards AGI.
And if we want to avoid creating AI systems that are just good at mimicking human behavior but lack true understanding.
And if we want to create AI systems that can actually navigate the world and solve real-world problems.
Well, this has been a fascinating discussion. It's clear that the UCSD result, while impressive, raises more questions than it answers. It highlights the limitations of current approaches to AI and the need for more interdisciplinary research. Thank you all for your insights. And thank you to our listeners for tuning in to Cognitive Spirals. Until next time.
Thanks for having me.
My pleasure.
Likewise.